Now that we understand transformations and our basic graph shapes, it's time to practice them. So I'm going to show you kind of a Leonard way to approach graphing with transformations. What we're going to talk about is basic graph shape. We'll talk about key points. We'll talk about labeling all of our transformations and then using our shifting of our x and our y axis to create this sort of new xy axis, putting our new key points, how to modify those, on the new xy axis and getting a really good graph. We'll talk about axis of symmetry if there is one. We'll talk about how to use that. And then we'll talk about how to make the graphs a little bit better. So let's get started. Let's take a look at f of x equals -1/2 absolute value of x minus 3 and then plus 2. One of the things that we need to do every time we're graphing with transformations is identify what our basic graph shape is, get a picture of what it looks like in our head, identify our key points, and then identify what transformations are happening. So when we look at this, we go absolute value. In your head, that's got to make a V. Now what we do with that V might reflect it, yeah, but the basic graph shape is a V. Then after that, we go, okay, that basic graph shape, because that's an absolute value type of graph, it is even in its most basic form. And then we're going to talk about our key points. So our key points are 1, 1, 0, 0, and -1, +1, because that's based on an even shape, an even graph shape. So we've identified our V, we've identified our basic graph shape, and then we're going to see what these transformations have done. So number one, we've got this plus 2. That plus 2 happens after the absolute value. That plus 2 says your output is being affected. So all this stuff is over with. All the multiplication would happen before you add. All the absolute value would happen before you add that 2. So that plus 2 is affecting your output only. So it says I'm going to affect my output. This is going to be a shift up. So we can put a vertical shift up 2 units. Then I look inside, I go, okay, inside that I'm affecting my input. That input of x is affected by subtracting 3. Now we know that inside the function, the horizontal shift, the affecting the input, is kind of opposite of what we want to think. So -3, it does not move left 3, it moves right 3. Now we look out front. That out front idea is also affecting the output, not the input. The only thing that ever affects the input is stuff that happens inside the function before you let the function take over. So we looked at it and said, that's an output, that's affecting the output, that's +2. That's affecting the input, that's -3. So up 2, but right 3. Now we look out front and say, okay, that's also affecting the output, but in a little bit of a different way. That's affecting the output value multiplicatively. So it's affecting it by multiplying the output by 1/2 and a negative. Now, practically, we treat those as one thing. So we're going to multiply this output in just a minute by -1/2, both of them together. But really, technically, that's 2 different transformations. The 1/2 takes your output value, doesn't change your input, that's already happened here, takes your output value for the given input, whatever you have, and then it's going to cut them in half. That's going to be a vertical compression. Vertical compression is going to make our graph look wider. That's what's going to happen. Also, we're multiplying our output by a negative. So we've shifted up 2, we've shifted right 3, we've cut the output in half. Now we're going to take the output values and we're going to reflect them. We're going to reflect them about the x-axis. So it's going to take the output values and change their sign. That's a reflection about the x-axis, altering the values of our outputs. Those would be the 4 different transformations going on in this graph. So if you want to write them out, we have up 2, a vertical shift up 2, we have a horizontal shift right 3, we have a vertical compression, we're shrinking output values, we have a vertical reflection about the x. Practically though, what we do with it, if you know what the shape of your graph is, that V, and you know what your key points are, then if we shift them up 2, we're going to move this axis. And we say we can kind of pretend our axis moves. If we shift this up 2, we're going to move our axis up 2 units. We're going to move our other axis, our vertical axis, over 3 units. Then we're going to take those outputs and say, wait, that -1/2 affects our output values only. The shifting affected our input values, but this -1/2 affects our output values only of our key points. We take those key points, we say, what's happening here? I'm finding an output. I'm multiplying by -1/2. My input value won't change, but 1 times -1/2 would give you a negative 1/2. Do you see this? Do you see how by multiplying your output values by the negative and the 1/2, you're doing both a vertical compression, shrinking the output, and it's also reflecting it. It's changing its sign. 0, 0 is never going to change by multiplying, but negative 1, 1 becomes negative 1 still. You never affect that input unless you start multiplying your input by something. That'll be the last example we do in this video. But your 1 times negative 1/2 is also negative 1/2. So here's the way that I like to do it. I like to do this in the same order we wrote them down. So we're going to shift our horizontal axis up 2. We're going to shift our vertical axis right 3. We're going to get this new xy axis, and then we're going to graph our new key points. How do we get our new key points? We multiplied our outputs times whatever is there. This said, multiply your output of your function times this number. We just did that. Here's our original key points, and we did that. So let's graph it. So let's see, up 2. And right 3. I showed you this in a previous video that when we move our xy axis, this is not really there, but it gives us a really good place for us to put our new key points. So this says you're going to shift your graph up 2. Great, let's show that. You're going to shift your graph right 3. Let's show that. This is like our new origin, not really there, but if we graph our new key points on our new xy axis, it's going to show us where our graph actually is. Please keep in mind, our key points, when they're graphed from our quote-unquote new xy axis, they're not the points 1, negative 1/2. I understand that, but it's where those points will be on your graph. Now you can interpret that and say, all right, this would actually be the point 4, 1.5. That's fine, and that's important, but this gives you a very good way to do it. So 1, negative 1/2, using the same scale that we had as our original xy axis, our key points would be 1, negative 1/2. So from here, this would be like our 1, negative 1/2 is about right there. We'd still have 0, 0 right there. We'd still have negative 1. This would be like our negative 1 on our new xy axis, negative 1/2. That's about right there. So what we've done, we've looked at it, we said this is a V. I got that in my head. I know what my transformations are. So I know what my key points were. I know what my transformations are. I'm shifted up 2. I got that. Shifted right 3. I got that. I am doing a vertical compression. I multiplied my outputs by 1/2. I'm doing a reflection about the x. I multiplied my outputs by a negative. We did that at one time. Now we graph those key points on our shifted axis, and we recognize this is not a parabola. It's not a square root. This is a V. It's just been reflected. So draw the V. And then if we want to make it a little bit better, that's a sketch. Want to make it a little bit better, understand that we can do things like find the y-intercept pretty easily. If we plug in x equals 0, so plug in x equals 0, 0 minus 3 is going to give me negative 3. The absolute value of negative 3 is positive 3. Positive 3 times negative 1/2 is negative 1.5. If I add 2, it's going to give me positive 1/2. So I found that value by taking 0 and plugging that into my function. That's going to give you a better graph. So my graph is a little off right now because I was curving a bit. Okay, that's way off. That gives you a better look for my graph. The other thing I can do, because this is an even function, you have an axis of symmetry that runs right through where that change from increasing to decreasing is on this graph. That's why I like this technique so much of drawing your new y-axis where that would shift to, because it automatically gives you an axis of symmetry. It's really nice. You don't get that if you don't do that. Well, if at this level of 1/2, we're how many units away? 1, 2, 3 units away from axis symmetry. Then 1, 2, 3 units away from the axis symmetry on the other side, we'll also have this height of 1/2. So 1, 2, 3, 1, 2, 3. We have a height of 1/2 as well. That gives you the ability to graph much more accurately than just a sketch. That gives you a really nice looking graph for minimal work. You have to plug in a lot of points to get that graph as accurate as we just got it by using our shifting. So one more time all the way through. You're looking at what your basic graph shape is. You're identifying your key points. You're identifying your transformations. There's 4 of them here. Practically, we kind of do 3 of them. So we do a vertical shift if there is one. We do a horizontal shift if there's one. Then we talk about an output affectation, this number in front here that's multiplying your output. We do those at the same time. Then we use our axes. We shift them up, down, left, right. We have this new origin. We plot our new key points after affecting them. We plot our new key points on that axis, or on the new XY axis. If we need to find like a y-intercept, do it. Just plug in 0 to your original function, no problem. That is a point on your graph. And then you can use your axis of symmetry, which you automatically show by using my technique to get a kind of a free point. So anyway, that's the way that this graph would look for sure. It is the V, it has been reflected, it has been squashed, it's made it a little bit, so vertical compressed, has made it a little bit wider, and we have our vertical shift and horizontal shift correctly. Let's go ahead, you should be trying that one on your own. See if you can identify what the shape of that graph would look like. Is it a parabola? What is it? What's it look like? Is it a V? See if you can write down your key points based on the fact that it's odd. See if you can write down the 4 transformations that has, up, down, left, right, compress, stretch, reflect, whatever that does, and then see if you can graph it. So I'm going to start right now. This is a cubic, so it's going to look like originally like this power 3 curve that we're hopefully getting used to. After we understand that what that looks like is odd, we know that our key points originally be 1, 1, 0, 0, and -1, -1. That's how every one of our odd basic graph shapes, that's the key points for every one of our odd basic graph shapes with the exception of the 1/x function. It doesn't have 0, 0, but they all have 1, 1, -1, -1. Why? Opposite outputs give you opposite inputs give you opposite outputs. That's how odd works. Now we'll go ahead and identify our transformation. So we have our key points down, we've identified our function. Now we're going to say, all right, well, let's see. This -1 happens after the function. It's affecting the output. It's saying, I want you to add or subtract. Here's subtract 1 from every output. That's a shift down. Inside says, I want you to affect the input. I want you to add 1 to every input before you put it through the power 3. That means that in order to undo that change of input, I would have to give myself smaller values. That's a shift to the left 1. I'm looking out front. This is 2 things. This says, I want you to squash the output values. I want you to multiply by 1/3. Cut them in 1/3. So cut them down. That's shrinking. That's a vertical compression. This multiplies by the output of whatever your function said. So I'm multiplying, that's shrinking it, cutting by a factor of 3. So shrinking it into 1/3. That's a vertical compression. The negative says, I'm taking your output again, but now I'm changing its sign. So are you thinking through that? Are you seeing the shift down, seeing the shift left 1, seeing I'm affecting the output and squashing it? Vertical compression, there'll be a horizontal stretch. Are you seeing that I'm making the output change sign? It's not an input change sign, it's an output change sign. It's going to reflect about the x-axis. Reflect x. Now, practically what we can do, that down 1 takes our x-axis and shifts it down 1 unit. Is it really shifting down 1 unit? No, but graphically we can use that. We're shifting our y-axis left 1 unit. Is it really shifting left? No, but we can use that as an axis of symmetry. And so now that we've shifted down 1 unit and left 1 unit, we're going to take a look at our key points and understand what in the world is happening here. Our key points are being affected. As far as their outputs, not inputs, there's nothing multiplying your input. Can't change. But your output values being multiplied by -1/3. Yeah, it's going to shrink them and reflect them. So our inputs don't change. That's 1, but -1/3, because 1 times -1/3 is -1/3. 0, 0 doesn't change at all. 0 times anything is 0. -1 doesn't change, but -1 times your new multiplying your output idea gives you positive 1/3. Look what your outputs are doing. It shrunk it and changed a sign. It shrunk it and changed a sign. In absolute value, shrunk it and then changed a sign. So 1 comma -1/3, but from our new XY axis right here. So from that new sort of origin idea, I'd go 1 and -1/3. So here's 1 and -1/3 is about right there. Then I'd have -1 comma positive 1/3. So from the same scale, this would be 1 unit, and then down 1 would be like right here. So 1/3 of that, I guess it's a little more kind of here. So 1 comma -1/3 and 1 comma positive 1/3 is about right up here. That's really taken the cubic and squashed it. It's also reflected it. So normally the cubic would look like this, like going through those points, but now I've reflected it and squashed it. So our cubic, according to the reflection that we had, according to the vertical compression we had, according to the shifts that we have, has a 0, 0, a 1 comma -1/3 based on our new XY axis. It's very squished. It's been reflected. We have a y-intercept, so we can't find that. You could make it a little bit better by plugging in a value like +1 and seeing actually where that is. So you plug it in and you go, okay, 1 plus 1, that's 2. 2 cubed would be 8. -1/3 of that would be -8/3. So -2 and 2/3, and then add 1 would be -1 1/3. So we know that this would go through, so this is off because it should be a lot flatter than this, but we'd have a value of that for that input value of 1. So you can make your graph a lot better by plugging in some extra points around that. But what you don't do, you don't start by just plugging in random points. You'll miss some key features of this. You'll definitely miss your transformations. So I hope that makes sense. I hope that you understand that, that the first thing we want to do is understand the shape. Then we want to understand our key points. We want to take our vertical shift, then our horizontal shift, if there are those. Then we want to take these, if there's 1 or 2 transformations, write down what they are, a compression in this case and a reflection about the x in this case, then use this in conjunction to multiply your outputs. That's the way we go about doing it. I'm going to come back with 2 more that are slightly more difficult. We'll talk about how we reflect about the y in the last example. Before that, we'll talk about the reciprocal function. We haven't done anything with that yet, so hang on. All right, let's continue. A couple of these are a little bit more difficult, and the reason why they are is because number one, we're not as used to working with square roots and with the reciprocal function as we are with something like an x squared or x to the third graph. So that's a little bit more difficult. The second thing is that sometimes you really have to modify what's given to you to sort of see what transformations you have. And so here's what I'm going to tell you to do with some of these functions. Number one, what we're trying to look for is on the inside of your function, so in the parentheses, in the square root, in the whatever you have, in the absolute value, we really want to have x first, and we need x to be positive in order for us to really see the transformations that are taking place. So when I look at this, you go, okay, well, what's the inside? The inside here is the inside of the fraction. Is x positive? Yes. Is x first? Yes, that's what we're looking for. This is going to give us an accurate transformation. However, we also want to see the original function in this. Now, this doesn't look like an x squared. This doesn't look like a cubic or a square root. It looks like a fraction. The only thing on our library of functions that has a fraction is 1 over x. Make it look as close to that as possible. So what I mean by that is the 3 is kind of messing us up. Sometimes it's a little bit better for us to write this as 3 times 1 over x minus 2 plus 1. Why? Well, it lets you see that's the reciprocal function. It's based on the reciprocal function, but it's having 2 subtracted from its input. Oh, it's got to mean something. I see a plus 1 adding to its output. I see a 3 times the output value. So that's going to be a vertical, whatever that happens to be. This is the way that we should kind of approach it. Make sure that the inside of your function has a positive x and that it's first. Try to make it look like the function that it's based on. So if this is 1 over x, try to make it instead of 3 over something 3 times your original function is just being modified. That helps a lot of students there. I hope that helps you too. So we're looking at it, we're going, okay, that's the reciprocal function. The reciprocal function has only two key points. It's odd, but the key points are 1, 1, and -1, -1. It's an odd function. All odd functions in a library function have those two key points, 1, 1, and -1, -1. Now we're going to go through and identify what's going on with this function. We need to look at it and go, okay, based on the fact that it's a reciprocal function, what's +1 do? That +1 is a shift up 1 unit. And you could write out the three transformations we have here. That's totally fine. This is a shift up 1. So I'd probably circle that and go, yep, that's up 1. Now I'm going to look at the -2 and say, all right, well, that's affecting the input. That says take your input value and subtract 2 from it. What would I have to plug in to get the same input value that I really wanted to? Well, I have to go 2 bigger. So that's a shift to the right 2. We talked about why that was in the last video. And you could write those transformations out if you're required to list them. So right 2, and I'm creating this idea of a new XY axis. No, it's not really on the paper, but it gives us a really good key, kind of a graphic organizer on which we can put our new key points when we finally figure those out. So we've shifted up 1, we've shifted right 2, and now we're going to deal with that 3. That 3 says, I want you to take the output of your function and multiply the output by 3. Not the input, has nothing to do with multiplying the input. There's no negative multiplying the input, no number multiplying the input. This says just take your output values and multiply by 3. So what's it going to do? Is it going to reflect them? No, that's not negative. Is it going to stretch them? Yes. It's taking your outputs saying that 3, what that does, you're going to get 1 comma positive 3 and -1 comma -3. It does not change your inputs, but it multiplies your outputs by positive 3, stretching this function out. That's what's going to happen here. So we're going to graph that. If you want to write the transformations, you'd have a vertical shift up 1, horizontal shift right 2, and you'd have a vertical stretch of a factor of 3. It's taking your output values and multiplying every single one of them by 3. Okay, so 1 comma 3, as it relates to this idea of a new shifted XY axis, says, yeah, the point 1 comma 3 is not really there, but if I graph it according to this, 1 comma 3 is like way up here. The real point is 3 comma 4. Yeah, that's true. And the other point, -1 comma -1, 2, 3. -1 comma -3 would be down here. That's also true. It's stretched this out. The real point would be 1 comma -2. But if we graph this according to our new XY axis, it gives a really good picture of the graph. So we're going to graph it, understanding it's going to be a little weird because we've stretched it out here. Now, what would make this better? Firstly, maybe hitting the point. Secondly, I don't know where this crosses the y-axis, do I? It's not going to be very clear. Maybe find the y-intercept. They give you a much clearer picture of what's going on. So if I want to find the y-intercept of this graph, I would plug in x equals 0. Take and plug in x equals 0. Go, wait, I can't have 0 on the bottom. You won't, because you're subtracting 2 from it. So 0 minus 2 is -2. 1 over -2 is -1/2. That'd be 3 times -1/2 is -3/2. Plus 1 is -1/2. So I know this is crossing the y-axis at -1/2. I hope I did that right. -3/2 plus 1 is -1/2. 0 minus 2, yeah, -2, -1/2, plus 1, -1/2. So this graph is going to look like something like that. It's not going to be perfect. If you wanted to find the x-intercept, it takes a little bit more work. To find an x-intercept, you'd have to set this equal to 0. And say, all right, 3 over x minus 2 equals -1. We could multiply both sides by x minus 2. Make sure you distribute. Subtract 2. This would cross at -1. And we'd get a better picture of that. So this graph has been shifted up, 1, right, 2. We've affected our outputs. We've stretched the graph out. That looks pretty ugly, but that's the way this graph sort of looks as far as a sketch is concerned. All right, the last one. This gets a little bit funky, and the reason why it is, I just told you that you want a few things to happen. Number one, you want to be able to identify your basic graph shape. That's a square root. We know that square roots look like this, just like the original reciprocal function looks like this. That's exactly what we got. Well, our square root is going to have some things happen to it, but to understand what actually happens, we really want to know what this looks like if our x is first inside your square root, inside the parentheses sign, whatever function you have, and if it's positive. So we have a little bit of work to do. For instance, I really don't like the fact that x is second. Really don't like the fact that x is negative. It's going to give us a misinterpretation of what this is. This is not a shift to the left. You go, wait a minute, I thought plus was left. Yeah, it is if your x is positive. So what this does, this says, all right, I have my function, I have my 2. If I factor out the negative, that is what you want. If you want the x to be positive, even if you have to factor out a negative, what that negative does, that changes the sign of your input is what that does. That's going to reflect this about the y-axis. That's what happens. This is actually a shift to the right, and then we reflect it about the y-axis. So when you're organizing your thoughts on this, try to see the basic graph shape, no problem. We're going to get our key points in just a minute. But when we organize the inside of our function to see some of the reflections, we want our x to be in order. We want this to be in order, but we need our x to be positive as well. That sounds very familiar, like factoring, because it's kind of based on the same idea. So let's go ahead and do it. We now know this is square root. We know our key points for square roots originally are 1, 1, and 0, 0. But we have a few things happening. And now we can see what happens because we've structured it correctly. We can see this has a shift up of 3 units. So we're going to graph that. We know this has a shift, so this would be up 3. This has a shift, not left 1, right 1. That gives us a great place from which to plot our new key points. So our key points were 1, 1, but what happens to them? Well, there's 2 things. Number 1, we had a shift up, that's our first transformation. Number 2, we had a shift right, that's your second transformation. But we have 2 more things going on. This negative inside our square root, that's affecting the input, inside input. It's changing the sign of your input. If you change the sign of your input, you start swapping on opposite sides of your y-axis. That's a reflection about the y. It's going to affect your inputs. So what this does, it says, okay, if I'm going to affect my inputs by changing the sign, instead of 1, I'd have negative 1. Instead of 0, well, I'd still have 0. Now what's the 2 do? The 2 does not change the sign of your output. It says, hey, look at your output. There's a square root. You'd have some numbers coming out of that. Now multiply them all by 2. So take your output value and multiply it by 2. So instead of 1, just multiply by 2. There are 4 transformations here. One's a shift up 3. One's a shift right 1. One is reflecting about the y-axis. That's what that does. It affects the input, change the sign of your input, reflect about the y-axis. And one is a vertical stretch by a factor of 2. You're multiplying all your outputs by 2. Can you see that in the new key points? Can you see that what this has done is change the sign of our input? That's what that does. This is multiplied our outputs times 2. That stretched it out. So we have our shift up 3, nailed it. Got our shift right 1, we got it. We're going to plot our new key points. Key points were 1, 1, now it's negative 1, 2. Key points were 0, 0, it's still 0, 0. Yes, the real point is 1, 3. I know that, but it's a great way to do it so that you get a good picture. Now, negative 1, 2, according to this new xy axis, -1, comma 2 is right there. It's right there. Yeah, the real point is 0.05. You know what? If you plugged in 0, we darn well better get 5. Let's plug in 0. 1 minus 0 is 1. The square root of 1 is 1. 2 times 1 is 1 plus 3 is, 5. Look at that. We have it right. If we plug in 1, we should be getting out 3. 1 minus 1 is 0. The square root of 0 is 0 times 2 is 0 plus 3 is 3. This is the proper graph, but understanding how these transformations affect your original graph is crucial to a lot of things we do in graphing, especially when you get to calculus and trigonometry. Understanding the picture of it, I promise you, you do not want to go plugging in lots of different values to a trigonometric function trying to graph it. It's insane, all right? You want to plug in negative pi over 6? Be my guest. Sine of negative pi over 6 is what? That gets very challenging to do that. And plot a graph, it's not challenging to get an output, it's challenging to plot a graph with those outputs. That can be very difficult. So understanding that this after a function means you're adding or subtracting, and that means that you're vertical shifting up and down respectively. And getting this organized so that your x is first and your x is positive, and now understanding that -1 means a shift to the right when I'm affecting an input. That's a shift to a right by 1 unit. And that negative inside is affecting the sign of our input, making it positive versus negative, and that's reflecting about the y. And the negative, this 2 outside is multiplying an output and stretching that, or compressing it in the previous examples we had. And negative would be reflecting about the x-axis. That's so important for what we're doing. So our graph finalizing this says, yep, it's a square root, but I've reflected it this way. I'm still going to graph my square root function. That's about how that graph looks. That's at least a good sketch of it. I hope that makes sense. I hope it explained the nature of our transformations and put them together in such a way that you really understand what's going on. It's a big deal. We really need to know what causes a graph to shift up and down. We need to understand that that's affecting the output, and that would be after the function is kind of done, after parentheses, square roots, and all that stuff. We need to understand how to shift left and right horizontally. That's affecting the input. But then adding to the input is a shift left, and subtracting from input is a shift to the right. We need to get that. It has to be in order with your x positive to figure that out, even if it's factor negative. We need to understand that reflecting about the x-axis is when I change the sign of my output value, the outside the function. We don't have one here, but in the previous 2 examples, that was what happened. We need to understand that outside the function, when I multiply it, is stretching or compressing because it's multiplying the output by a value. We need to understand that reflecting about the y-axis is affecting the sign of the input. So those things have to kind of be there. We need to list out our transformations. I hope I've explained in such a way that you know how to do that now. So we're done with graphing for until we start talking about quadratics in just a little bit. So I hope that you enjoyed the video. I hope it made sense. I hope to see you for the next one.